I need to do by myself, okay? So yeah, so let's start today's lecture about the project overview and also show you some strategies about how to do the project. So I think what I want to kind of promise you is I think because of this lecture or this course is a project based learning, right? So project-based learning, also called experiential learning, right? So you learn by kind of like doing something, right? You learn by doing something. So what I want to kind of promise you is even we cannot meet in person to do the projects, but actually we figure out some very exciting projects for you. You can also do at home, and it's not very easy, but we will break down to different like labs and homeworks, so you can do that step by step. So you can learn something very useful, but it's also not very difficult for you to learn that. So let's get started about today's lecture. So first, I will talk a little bit about my lab research, and then I will talk about the Mechatronics kit. Then I will talk about the final project you will do. This is kind of like the main topic for today's lecture. And then I will talk about how you can actually accomplish a project, some like a project formulation. And then we have like a homework too. And each homework is generally due 2 weeks from the assignment. It's just for homework 1, right? So I give you 1 more week because I assigned this last week, but you can turn in the homework through the Dropbox link, right? So we give you a link, don't email us. So for all the submission, there's a Dropbox link. You can upload the files, right? So I prefer if some of you can turn on your camera. So hopefully I want to see you. So have a little bit of interaction, right? So if anyone, most of you can try to turn on your camera. So I prefer to see you. And if you have any question, feel free to stop me at any moment, right? Before I go to the next slide, I just want to show you some tricks about how to, it's kind of like a relate to the homeworks, but all the homeworks, right? So let me see if I can do it. Okay. So you know, for homework 1, right? So I asked you to read 2 papers and produce 2 summaries, right? So 2, right? Make sure it's 2, right? So I think in terms of paper, right? I asked you to read, right? So it's kind of like I typically want to use a stair model. It's kind of like a staircase. By that I mean, let's see if I can tune this. By stair model, I mean like actually for the stair model, I mean if you read this paper, right, it's kind of like this way. And you know, you probably heard like what Isaac Newton said. What he can do is standing on the shoulders of giants, right? Basically, even his work is based on previous work, right? And so the current paper, right? So the paper assignment is like this, right? It's called a literature, right? Literature, right? Either literature or kind of like a prior art, okay? But we want to do it better, right? So we want to reach to this kind of like a level of technical readiness, right? We want to get it better, right? So this is our goal, right? This is our goal, right? So we want to make something as good as this technical level, right? So if you think about the vertical line, right? So we want to make this. So this, right? It's kind of like a staircase, right? So this called a what? Called a gap, right? So in the report, right? In your summary, right? In your summary, I want you to clearly describe, right? This is number 1. kind of like a prior art, or also called
Yeah.
Michael's outside.
All right.
state of the art, right? So also called state of art, or called prior art, or also called literature, right? So whatever, it's the same thing, right? And so
creators were making 4K movies.
So when you do this, right? So I talk about this stair model, right? And the stair, this is kind of like a state of art, right? So you should understand what's going on in the state of art. Then we want you to understand the goal, right? For example, we want the robot to be lightweight, right? Really lightweight to really help a human to save energy, right? Let's see. Reduce energy, right? So this is like a Iron Man, right? This is a current robot, right? And there's a gap. So what's the gap, right? So what's missing there, right? Maybe the robot is too not smart enough, right? Maybe the robot is too heavy, right? Whatever. You make sure the gap is clear. Then you also, from the paper review, you want to say, okay, what's the new solution in that paper to make the robot better, right? So this is a stair model, okay? Any question about this stair model? Okay, if not, I will move to the next section, and let's go over to the details of today's lecture. So again, you can find this from this link and all the files. Actually, you know, I only want to share you with a Dropbox link, right? And you can say, for example, I think if you only see this Dropbox link, I think you get everything. And let me close this one. So I actually already give you the Dropbox link, right? The Dropbox link is to this folder. Under this folder, you can see the lectures, right? You can also see the homeworks, right? So one link, you can get everything, right? So this is the link to that folder, right? So I will post this in Blackboard, but generally it's already, the material is already available there, right? So I think that's kind of like clear enough, right? So feel free to stop me any moment, right? And let's go back to the lecture and switch to the view. And so you can see, okay. So I want to talk about a little bit about MyLab research. So you can get kind of like some sense what MyLab does. And also is one representation about the state of art of robotics, right? And for example, we develop kind of like enabling technology and robot platforms, right? And on one hand, we do, when I talk about enabling technology, I mean like actuators, sensors, and those kind of like basic components, right? And we also work on like robot design. We design robot from scratch, right? So we don't buy robots, we design it by ourselves. When we also develop some like a controller, which is some like a smarter algorithm to make the robot like like some students said, AI powered robotics, right? This kind of like AI stuff, right? So I really want you to remember this diagram because this called do you know what is this called? It's called what? Anyone in 411, you know this called what? Do you remember what's this diagram? Any?
Is it a box diagram?
Block diagram?
No. Anyone from 411 knows what's this diagram? Anyone else? Most of you learned the 411, right?
I don't know. It looks like a flow chart to me.
It's called
Motor control.
closed loop. Right. So I think you probably don't appreciate this, right? And you probably don't, okay, think, oh, it's a flow chart, right? But for you, who already took a 411, right? You should know this called a closed loop control diagram, also called feedback control, right? Feedback control diagram, right? So, you know, what I want to share with you is, I think I really want you to remember this, because this, I think this is the most important diagram in robotics and control, right? And, you know, when you start to work on robotics, you really appreciate this diagram, because it really tells you the big picture, how a robot works, right? And how, yeah. So on the other hand, we also, so this is kind of like on the left, kind of like, you see, this kind of like, we call this kind of like the domain on the left is called a robotics, right? So this is robotics, right? This domain, right? On the right, we call it scientific discovery. So we develop some like robots. We call the bio-inspired robots, like a bio-inspired exoskeleton, for example, right? And we learn from medicine and understand some problems, right? And I told you, right? We want to understand the gap, and we develop some robots. On the other hand, we also use the robot as a tool to study, right? To investigate the medicine, right? To study how we can do better about solve some like a medical problem, right? Like help people to walk better, right? We study augmentation for able-bodied people, right? And also rehab, right? For people with disability, right? So that's my lab task, that's our research. So we actually cover a very broad spectrum in the continuum care, from like disease prevention, for example, this exoskeleton, to prevent musculoskeletal injuries for people, for workers. Yeah, I really want to just show my head, but kind of tricky. We also work on some like MRI compatible robots, MRI compatible robots that can do neurosurgery, brain surgery, or prostate biopsy, right? So POCA does the biopsy through robotic needle placement. We also work on like an exoskeleton that have like a recovery and home care, right? You see, we want the robot can be used at home, right? In home setting. But right now, most exoskeletons can only be used in lab settings, right? So they are not really designed for home applications. So that's a gap in this research area. And that's what we are trying to make that better. And we use a soft robot approach. So it's a lightweight, more comfortable, and for both adults and also for children. Right? Any question?
Nope.
No? Okay, so far so good? Okay, cool. Yeah. We study kind of like there are two types of robot. Right? There are many ways to classify robot. One way is a rigid robot. The other is a soft robot, right? So that's kind of like a simple solution, right? And this kind of like rigid material robot, right? I think you have seen some like industrial robots, right? It's a metal linkage, right? Which is made from like a rigid components, right? So it's called a rigid robot. But a rigid robot, like this exoskeleton, right? You can see the person is wearing exoskeleton. This is a linkage. This is another linkage. One linkage on the side, one linkage on the shaft, right? And then there's a joint here. It's a rigid robot. The material is rigid, but they can be kind of like a compliant, right? So you can kind of like move it, make it a pretty compliant, right? It's rigid, and but you can make it behave with some compliance, right? So inside this robot, we have battery, right? In the back, the person carries battery, also has the motors, and somewhere here, the motor is here, right? Drives it, right? And then next to the motor, right? So there's a motor, and the motor also is attached to some kind of gear, right? Gear is typically a pair, gear 1 and gear 2, right? So this is called a transmission, right? And in the end, the robot needs to carry a load, right? In this case, what's the load? What's the load of this robot? This is the exoskeleton robot.
The human?
The human, right? Can you be more specific? Human what?
Body.
The weight of the human?
Kind of. More precisely is so. Yeah, exactly. Someone said that the limbs, right? The robot limb, right? Sorry, human limb, right? So the load in this case is a human limb, right? So the robot drives a human limb, right? So that's the load in this case, right? And but it's certainly a nice robot. It's developed about 10 years ago. I think 2011, around that, and 10 years ago from Vanderbilt University. Right now, it's a commercial product. And so this is a recent version, but the original version is a very old, about 10 years old. But there's one limitation. So if you think about this, the robot linkage, right? And you think about the human joints, right? There's also human joints. What's the limitation? There's something like one problem with this rigid robot. Can you think about some limitation of this robot? You can roughly see the robot, right? So it's kind of like
the angles that it can, turn and.
So
It won't be
about,
exactly in his joints or something like that?
Can you say that again?
Like it won't be exactly where the joints would be or something? Like it won't be.
Yeah, very good. Yeah, thank you. Good answer, right? So say it's difficult to align human joint with the robot joint, right? Think about that. If you just attach two metal pieces together, right? And with a linkage in the middle, right? And you attach that to your knee to attach those two linkages, right? To yourself, right? This link and this link, right? These two links, right? Do you feel very comfortable? Very likely not, right? Because it's rigid, and also there's a joint misalignment. You see, it's really hard to align this joint with the human joint, right? So it's pretty tough to align them together. Or let's say it's impossible because a biological joint, human joint, is more complicated than a simple robot, like a revolute joint, right? This is called a revolute joint, right? So it's just a hinge, right? So to solve this problem, right? So as I mentioned, there's a second category of robots, right? It's a soft robot, right? And let's see, uses. So soft robot and called soft materials, right? And because the material itself is soft, we can use rubber, fabric. This is the most popular research area in robotics right now. So I think, for example, in this case, this kind of like a crimson color, red piece is made of like a rubber elastomer. And this robot, kind of like it's not very easy to see. It's kind of like a air blender. So it's kind of like an air, kind of like a balloon, right? So a balloon, right? Balloon-based robot. Because so why this kind of robot has this issue? Why? This is not good, right? But this kind of robot is good. Do you know why? There's no joint misalignment issue. Any idea why it has this nice property? Any idea why the soft robot doesn't have this joint misalignment issue?
It's malleable. It changes shape.
Yes, it changed the shape, but why?
It assists the movement of the person.
Yes, but
Elastic?
it's elastic. Yeah, it's elastic is one reason, but could it be more specific? Why?
The material characteristics of this material is better than what the other one is.
So you see, as I mentioned, right? In this case, you have a robot joint and a human joint. This is the issue, right? Right? This is a robot. This is human, right? But in this case, why it has no this issue? Why? You can see the feature of this robot, right? It's kind of like a rubber piece, a piece of rubber, a balloon, right? Why balloon is better?
Because it can adapt to the shape that you're looking for, rather than a rigid, you know.
Yeah. So that's a pretty good answer. So let's see if my answer is maybe more specific, right? The reason is because for those robots, there's no joints, right? There's no rigid joints, right?
Wait, there's no rigid what? Oh, joints. Okay.
Right, no joint, right? Because it has no joint, right? In this case, there's no joint misalignment issue, right? You don't need to align joint because there's no joints, right? So that's the beauty of soft robot, right? So by thinking of this, right? If you look at the kind of like a state-of-the-art soft robot, right? And they have like a different, so there are many different kinds of like a soft robot. So anything that you can imagine, any rigid robots, and you can essentially make a soft robot version. But there are several major limitations of those robots. First, you see, it has like a pump here, right? A big pump, right? And it needs an air pump to drive it, right? And here is the air hose, right? So to drive this. The second limitation of this robot, what's the limitation of this robot? Can you see the limitation of this kind of like a squishy crawling robot?
It doesn't seem like if it were to have a load vertically, it wouldn't be able to sustain it.
Right. So
because of the weight.
Weak, right? And also it's slow, right? And if there's any emergency, you want the robot to come and do some rescue, you probably don't want to rely this kind of robot, right? It's too slow, right? So yeah, so that's exactly, I think, the limitation of those robots. I'm trying to switch to, I can only see myself because it's kind of hard. No, still. Okay. Okay, that's fine. So the first limitation is tether, right? They all have a tether, right? It's tether, right? And it's slow, right? It's slowly crawling, and also it's weak, right? And those are the limitations of soft robot, right? So let's look at the exoskeleton in details, right? So why we need a robotic system? And from this figure, from this video, you can roughly see, right? This is the manual. This is the kind of like the manual procedure, right? So so this is a manual procedure, right? Can someone answer why we need this robotic device instead of this manual? Why? What's the benefit of a robotic device in terms of gait rehabilitation? Can you see the advantage?
Perhaps because some people that are disabled don't have the physical strength to be able to move and use the one on the far left. And so the one on the right, I guess, would be, I guess, a precursor to the one on the left.
Yeah, so that's the one benefit, right? Another benefit is, in this case, how many people are here to help the person to move?
Three,
right? You know, it's expensive, right? And also is labor intensive, and you can only do this in a clinical setting, right? And this is also true for so you can only do this in clinical setting, right? So that's why we prefer a robotic device, right? So robot have some like benefits. So we can, if we can use the robot to do this, right? We probably only need one physical therapist to work with this person in this case, right? And in this case, and you can see the video, right? And this is still kind of like a state-of-the-art research, right? And even they are not very new, but generally shows that. So this is bad, right? We don't want to do this, right? There's too many people, and takes too much time. You need to go to hospital and the clinics to do the rehabilitation, right? And here, this is better, but only one person, maybe two people, right? And in terms of this is kind of okay, right? But you still, this is about like 30 kilograms, right? The robot, the mass ranges from 15 kilograms to 30 kilograms, right? That's like 30 pounds to 60 pounds, right? Super heavy, right? So this is not good, right? So this one is a modular, only has a knee joint, right? So this is lighter, but it's still about 10 kilograms, right? So you can see it has some like advantages, but the main disadvantages and of this robot is that it actually costs more energy for people to walk, right? So this is the problem, right? So we want to reduce the metabolic cost, right? So we want this to be small, basically the energy, right? Energetics. But for those robots, there's no metabolic cost reduction. So those robots is like exercise machine, actually make your walking more difficult. It's only useful for people who are fully paralyzed. They cannot walk. So they can still, for people who cannot walk, this is useful, right? Because the machine can walk for the person. But if you wear this kind of like, let's say 15 kilograms, right? And 30 pounds robot, wow, that's too heavy, right? So what are the key challenges, right? And I think I decided it's too heavy, too much friction. So when you wear it, the joint, you can barely move the joint, right? So the robot is not compliant. So by this, I see it's not compliant. So you can feel a lot of friction from the robot. And the robot only moves when it's powered. When it's powered, it can move, right? So that's the limitation. And also we mentioned joint misalignment issue. And then in terms of control, it enforces the person to move around. So that's also a limitation, right? And so enforce the person to walk. It's not nice, right? We want to assist the person to walk, right? We don't want the machine to walk for you, right? We want the machine to walk, help you to walk, right? So that's the kind of like a minute difference, but it's very, very important, right? In my lab, we develop several exoskeletons. Sorry, let me reshare this video with you. So we develop several exoskeletons. Then we really want to optimize a lot of like features. So the number one thing is we want it to be really, really lightweight, and so people can wear this robot at homes, right? So lightweight, and the metric we use is like the mass, right? We want it to be lightweight, but we also want it to generate some torque, right? And sufficient amount of torque to help people to help people to walk better, right? And so it's not only the mass, but we also care about normalized mass. We normalize the torque by the mass, because for each kilogram of the robot, we wanted to maximize how much torque it can generate, right? So essentially make this really lightweight, right? So that's the goal we want to achieve. And the end goal is that we want to reduce the metabolics, right? Metabolics or energetics, right? So we predict that our robot, because you see it's about 3 times torque density with this robot from Harvard. So, but we estimate it can reduce about 4 times energetics in comparison with this robot from Harvard University. So yeah, any question? So let's watch a video. So
we have invented a hybrid exoskeleton that is softer, powerful, and smart to help patients to regain mobility. Our robot combines the advantages of rigid exoskeletons and softer exosuits. Motors deliver power through soft cables to variable structures to assist both flexion and extension motion. This is the first exoskeleton that is ultra lightweight with near zero resistance to human motion, thanks to quasi-direct drive actuation that use high torque motors with small ratio gears. The variable part is customizable using 3D scanning and 3D printed carbon fiber. Therefore, the robot fits the user very well, and it can be worn under clothing. Besides the adult exoskeleton, we also invented a pediatric version, which is purely textile-based and mimics the quad muscle. The raw material cost is under $50.
Our medical center is the clinical collaborator with Dr. Su's lab. Soft EMG sensor technology is a human-machine interface that monitors the user physiology and varies the power assistance by maximizing the use of the residual or remaining function. Our group plans to conduct the safety and efficacy studies to investigate the usefulness of this technology. This new robot offers a suite of important enabling technologies, from sensors and actuators to AI for a variety of patients with lower limb paralysis. The most promising aspects about this innovation is not only the technology itself, but the translational value, the potential for affordability, and the way that the device will encourage user independence.
Yeah, I hope you get some sense of how the robot works. And we also have this portable robot that can move forward, backwards, and when it's powered, and they can also walk a couple of different terrain, right? So different, like a very home-based application, right? So then I want to talk about switch to the about kind of like mechatronics education. And as I mentioned, we really promote projects-based experiential learning. And we developed this open source mechatronic kit and also website. And yeah, so we really want to we are also develop like 3 soft robots, including this soft robot hand, robot cheetah, and like underwater soft robot. So if you go to this website and assistive robotics toolbox, and you can see related information. Or you can go to my website, and I have the link to this website. In the last few years, we received a lot of like awards, including international and national awards. And so more than welcome for you to submit like papers or competitions, right? And then I want to talk about the Mechatronics kit. For the kit, and this is our first version. The second version we developed last year is a modular. So this is a modular version. And the current version is we are using this kind of like a commercially available kit, but it's a commercially available, but we come up very smart idea to do some this kind of like products. You can do it at home. Some nice projects we did before, for example, this origami robot. We call it this like an origami robot that is a foldable robot, can generate a high force. It's a high force software robot. Also, we use this robot designed like a exosuit. It's soft because this structure itself is made of fabric and it's pneumatically driven, and we made a vacuum pump so it can draw air. And the students even made like a custom circuit board, very nice system. And if you go to the website, and you can find the related information there. And there are several products on the website. So this another product is a hydraulic artificial muscle, hydraulic robot product. It can generate really high force, but a very lightweight. And we this is another product. This is kind of like an early version of this product. Maybe I briefly show you this video. Yeah. So students they designed this in last semester. Any question? So they designed all those kind of like pumps. The pumps. Sorry. They designed the pumps, and there's also a microcontroller on the right side here. Right, so you can roughly see a microcontroller. They designed the microcontroller. They developed the coding for the microcontroller. They designed this hydraulic artificial muscle, and they also integrate all components together. So they show that it's very capable to generate high forces with this robot. So they also, you say, they made some very impressive demos. So I'm really proud of this team, what they did, right? And so what you will do for this year, and we came up some very kind of like clever robot product. So it's a powered elbow exoskeleton. So it's a printable robot. So you can 3D print the hardware, and you will learn about motors, learn about torque sensors, and different like position control, torque control, and virtual kind of like a virtual wall controller, right? So this is like a Mechatronics. This is like a controller, and also use inertial measurement units, MU sensors, and to detect human intention. So I think it's really, really a cool product that you can learn something new. Even it's doing a remote learning, right? So you will do those work, right? So design the elbow exoskeleton. Some like you need to practice SolidWorks. This is one thing you need to do. Also assemble and test the exoskeleton, right? So we prepared several labs, so you can do that. And we also will teach you how to do the position control and torque control of those robots. And yeah, a lot of different new controllers, right? And also we will teach you about how to use the MU sensors and use the MU sensors to detect the human intention. Yeah, and as I mentioned, feel free to attend competitions or like submit conference papers, right? Whatever cool opportunities you can learn from previous year's projects and competitions. Yeah. Any questions? Okay, then I will talk about how to formulate the project, right? So this is maybe the most important slide for today's lecture. So I really want you to pay attention, and I will also ask maybe 2 or 3 students to go over this slide after I finish this slide, right? So robot design, right? It's not easy, right? Because it's like a open-ended project. It's kind of like an open-ended, right? Open-ended project, right? So you can design a big robot, you can design a small robot, you can design a robot for yourself, maybe you can design a robot for kids, right? So there are many ways you can accomplish a nice robot project, right? But I think it's like a system engineering, right? System. By system, I mean, it's not one component, right? It's not you design a mechanical system, right? It's not a one component. It's not a 2 component. It's a mechanical system, electrical system, and also kind of like computer science. You need to combine all those like kind of like 3 domains together, right? So I think that's the challenge, like how to do that, right? So I think all the projects should start from design requirement, right? Understand the design requirement is super important, right? And the second step is to let's see. The second step is to understand. Let's see. You will have some like a concept, right? Then you come up some like a basic design solution. Then you come up with some detailed design solution, right? In the end, I think you will do the manufacturing. But before you do the manufacturing, right, you need some kind of approval from me so we can print the robot for you. But the caveat for you is I do not want you to, I don't want you to just tell me, okay, I wanted to print this, right? I think it's not a good practice, right? Don't jump to this. No, don't jump to this directly, right? Don't jump to this detailed design, right? No, right? The right step is from step 1, 2, 3, 4, then continue until the last step and the system integration, right? So that's the key idea. And I think that this maybe sounds simple, but I think many people still don't quite understand that. Even many of my students, my postdocs, they don't quite understand how to do system design, right? So I will ask the 2 students and go over this slide, right? And explain to me what is in this slide, why it's so important, right? I think in terms of this order is super important for you to manage any like robotics projects. And I think it's super useful for you to go over through those steps. Can 2 students, I need 2 volunteers, maybe one by one. So to go over this slide, can someone go over this slide? Ramesh, can you do it? I need 2 students.
Do you just want people to read from it?
Not really read, right? Based on your understanding, and you explain this slide, right? Can you, Luis, can you explain it?
Perhaps I could try.
Yeah, give it a try, please. Yeah.
So for design requirements, it would be like what you need the thing to do. Right. So like all the necessary things it has to do to actually be helpful or work.
Right.
And for design concept is more like an idea of what you can do to make the project work. Like you can use this, you might be able to do this.
Right.
And then for basic design would be like taking one of those concepts and like trying to trying to work something out, an image, maybe a design for it that can work, but you're not sure of yet. And then for the detailed design, you can go more into the basic design, like work out how that's gonna work, how you can make, for further the design so that it satisfies all the requirements. And then for manufacturing approval, I suppose we gotta ask you or other people that know how to do it if it's possible to be manufactured or work out a way that you can get it manufactured.
Right.
Then the system integration test, I'm not really sure about that, but it would probably be the testing, maybe programming or anything that might need it. And that's basically all I got on that.
Okay, very good. Thank you. Yeah. So I think the key idea is don't jump to the detailed design, right? And right, don't do this right away, right? You should start from the beginning, really understand the requirements, right? And no matter you do this project or you go to a company and work on some projects and engineer, I think it's super important to know the design requirements, right? You want to make a small robot, a large robot, the robot to have an older person or a young person or a child, they are not the same, right? Don't just assume, okay, wow, I roughly know the design, right? So make sure you understand your design requirement, and even maybe, maybe come up with a table, right? And go over with your boss, right? Don't be shy to ask the questions, especially when you start your career, right? In this case, you can use this project to emulate as your first job, right? If I tell some chief engineer tell you need to do this, right? Make sure you understand the design requirement, right? Then you can start the design, right? But when I talk about the design concept, how can you do the design concept? What software you can use? Can someone tell me what software you can use to do the design concept?
You can use Simulink.
Simulink, okay. Anything else?
SolidWorks.
Yeah, SolidWorks. Anything else? What other software you think could show a concept, show some like a basic drawing? What you can use?
AutoCAD.
AutoCAD. What about the PowerPoint? Right. So for example, if I want to design an elbow exoskeleton, you can draw something, right? A linkage 1, linkage 2, right? You can draw something like this, right? And because this is rigid linkage, right? You can draw this linkage 1 and linkage 2, right? And okay, I probably ask you one question. Where do you want to put the sensors, right? So you probably will tell me, okay, if this is a robot, right? For example, this is a robot, and this is a human joint, right? This is a human, right? So this is a human arm, right? Let's say this is a human, right? So you can attach this to the human, right? Through some like a Velcro, right? And but where you should put the sensors, right? So that's something you need to design, right? You can put a sensor, maybe let's say this is a sensor. You can put the sensor, right? Let's put a rectangular, right? You can place the sensor on top of this robot, or you can place the sensor on top of the human arm, right? Right? So there are many options, right? But before you actually design this, before you do this detailed design, please do this, right? Come up with some simple design in PowerPoint or SolidWorks. So your team, right now it's only yourself, right? But the team or yourself can understand the general idea, and so you know how to design that, right? So this is a rigid robot, right? If I want to do a balloon type of robot, right? So just know this kind of like a linkage, right? And it will be kind of like a balloon, right? Just some kind of like a balloon, right? So just an air balloon, right? So maybe attached to human arm, right? That's what you see from the last few slides, right? So there are many kind of like design solutions you need to decide when in the we don't want you to do the projects in groups. the reason is easy to understand, right? We want to minimize the human contact, right? So I think we don't want to ask you to kind of like work together, right? So I think Louis already answered this very well. I think I probably will not ask the second student to go over this. But the key idea is do not do this right away, right? Does that make sense?
Hey, Professor, I got a quick question.
Yeah.
So you're saying that you're going to 3D print this for us? Is that what you're saying?
Yeah. Yes.
So we send the drawings to you, and then you'll 3D print it.
So Canon, yeah, I can print it, but you need to go through this process, right? So don't just send me an email to ask me for approval. I will not approve that. I will ignore your email because unless you show me this, right? You know, I'm generally very responsive to student email, but if you only do this, if you don't do this, just send me some CAD model, I will ignore your email, right? I will do nothing, right? Because, and I said, this is the most important slides for today's lecture, right? Go through the design steps. Maybe I think I kind of change my mind. Maybe I want one student to really kind of like, Sylvia, can you explain this diagram?
Sure, yeah, okay. So first since this is an open-ended project, we had to choose like the user that we're going to design for, such as a child or an adult. And then we can also make up other design requirements, such as the cost or the size.
Right.
And then the next step is to consider the design concept. So after doing some research on the background and ideas and like learning a little more about the foundation for this class, then we'll pretty much draw like a simple concept design using either SolidWorks or PowerPoint or AutoCAD. And then for basic design, we pretty much add on to that. And when we go into detailed design, we'll consider manufacturing drawings that will include like fasteners and other components that we may use, such as a microcontroller. And then after making manufacturing drawings, we're going to compile a report to send to the professor with all the previous steps and to get manufacturing approval. However, in the report, we also need to include a plan for the system integrations test. So for after manufacturing approval, we'll pretty much get the 3D printed prototype, and then we can do a system integration test on it.
Yeah, very good. Yeah, thank you. So I just want to make it very clear. When I talk about design, this is not only about the mechanical design. This includes a mechanical design, electrical design, computer kind of like a programming, right? So we will teach you all the steps. So don't be panic. And so keep in your mind, robots include the 3 components, ME, EE, and CS, right? So that's kind of challenge, especially for ME student, right? So you need to understand some like E stuff and also some CS stuff, right? But that's also very interesting for you to learn something new, right? And again, don't jump to this first, right? Again, I really, actually, I have been repeating this for several times, but I'm pretty sure some of you will keep doing this, right? So, you know, try to avoid this, okay? So
are we, sorry, Professor, are we putting, I guess that's what the next slide is. Are we putting deadlines on when we need to be done with what? Okay, I guess you're gonna go over that.
Yeah, so we don't, I set up some like milestones. So we will go over some milestones with you, right? So we will do some like, for example, we will start the project, right? So, sorry, I already told you the project, right? We will start the project and then you will do some background research. And actually, there's a company in Switzerland, sorry, a university in Switzerland. They already made a exoskeleton called EDU Exo, called EDU Exo. It's made in in Switzerland, right? So you can go to their website, but we are actually improving their hardware And so we are having our CUNY version. So feel free to check that, but I just want to let you know, right? So this the rough, any questions? So feel free to talk. So if you have your own 3D printer, feel free to print it. It's better you print it by yourself. But we have to do individual product. And because, to be fair, right? Because I know some of you probably are working together for 3 people, but I cannot ask all students to work together, right? So we cannot do kind of like, some people are individual, some people are a team.
Wait, so this project is a group project or a single project?
Individual.
Oh, individual. Okay.
Right. So, I'm not against you. For example, 2 people or 3 people work together and do the project together. But in the end, it's an individual project, right? I actually encourage people to have some kind of interaction, to learn each other. That's totally okay, right? Totally actually encourage. What I don't want you to do is, in the end, you need to make sure it's individual project. You need to do the individual labs. So everything in this course is individual. That's different from last year, because last few years, we have like a group projects because the projects are kind of difficult to do. Now, due to COVID-19, we have to do this kind of like a group, individual version, right? So I want you to think about some strategy. And so yeah, I think I probably will skip this because this is a little bit kind of like I can cover this in the next lecture. So I already talked about it a lot, but I still want you to think about kind of like your project strategy. How even it's a elbow exoskeleton project, but you have a lot of like how to say, it's an elbow exoskeleton product, right? So those are the components you need, right? And we probably even need to buy some like screwdrivers for you, right? So really think about how you can make this product working, right? So our default version is use some motion sensors to detect intention. But if someone wants to use some muscle sensor called electrical myography, EMG sensor, it's okay, but not quite encouraged, right? So my point is you can do whatever you want to do, but I generally don't encourage this because, it's an individual project. I cannot meet you, right? It's kind of hard for me to debug some like a hardware problem at your home, right? That's almost impossible, right? So basically, let's follow the same project, and we do that together through different lab, through about 6 labs. And when I talk about like the unmet needs, right? For each project, you can think about the requirement, the state of the art, right? So this is a gap, the step model, right? I talk about the step model, staircase model, right? So this is kind of the gap, right? And this is kind of like the requirement. What do we want, right? So this is the state of the art, right? So the kind of like a limitation of the current solution, and the requirement is this, right? What do we need? And the gap is here, right? And the gap, and this is a technical solution. So you need to come up with a solution to accomplish the project, right? So I think I will stop here, and let's share screen with you again. So I will stop here, but I want you to watch a video, some very cool video from one professor. So I think this could be a very cool video. I'm not sure. So there's some bug with my, there's some bug with my computer. So I'm going to, Selena, can you share the video with students so you can play from your end?